Hey guys, welcome to the next Diels Alder video. So in the previous one, we talked about how electron donating groups and withdrawing groups affect the orbitals. Alright, now I know everyone hates orbitals, sorry, but it's definitely something you guys should know about Diels Alder, because they could ask you a question about how donating groups and withdrawing groups affect orbitals. Alright, don't skip this stuff just because it's all about orbitals and everyone hates orbitals. Alright, so we talked about the electron donating groups and withdrawing groups, but we didn't talk about how they work in reactions. We just said a donating group on the diene speeds up the reaction, and a withdrawing group on a dienophile speeds up the reaction. So what would be the product when we have the donating groups and withdrawing groups, right? So we know that this right here, this is the easiest Diels Alder, right? And we react that usually we just put heat. And right, we have like these dashed lines. And we're going to get this as our product. Right? If you guys, I don't know, if you're having a little trouble with the formation of the product, I find it just easiest make that 6-membered ring. And when you have those two double bonds, right, all you do is wipe it away and put one bond in between where those two, in between those two carbons. All right. So how does this work now with an electron withdrawing and donating group? So first, what are some donating groups? A donating group is anything that puts electrons into our system. So let's say I attach this OCH3, this ether group. Remember, the oxygen has two lone pairs. So the way we can tell if it's a donating or withdrawing group is resonance. All right. Remember, this orgo is a pretty cumulative topic, right? So all the stuff, resonance, steric hindrance, please know it. So we can't take this double bond and resonate it up to this oxygen, right, to form a bond with the oxygen, because it has a full octet. If I draw out all the bonds, it has 1, 2. So there's 2 bonds, 4 electrons, 6, 8. Full octet already. So you can't bring that bond up, but what we could do is bring a lone pair down to form the double bond. Now the problem is this carbon has 1 bond, 2 bonds, 3 bonds, and a hydrogen, right? So we don't want to destroy that octet. It has already a full octet. So what we're going to have to do is move that double bond that we have there. So this is going to come down here. But now again, another problem. This carbon has a hydrogen, a bond there, a bond there, and a bond there. That's 4 bonds. Again, full octet. So what we do is move that double bond again. The only option we have left of how we can move that double bond is to put it on the carbon at the end in the form of a lone pair, like this. So the resonance structure of what we just drew is going to be something like this. This is the 1 lone pair, gets a positive charge. This guy is going to have this double bond here, and now it's going to have a lone pair on this carbon, giving it a negative charge. So this has a negative charge in that carbon. So you can see that in one resonance form it was neutral, on the other one it's negative on one of the carbons of the diene. That's what you want to see. An electron donating group should put electrons onto one of the carbons part of that diene, right? That conjugated pi system, which are these carbons. So this is how an electron donating group works. And we established that this OCH3 group cannot be a withdrawing group simply because we'd break an octet. So it can only be a donating group. So that's how that would work. Now, we can also have a donating group on this position. There's really 2 positions you can have a donating group. At the end of your diene, right? Doesn't matter if it's at the top one or bottom one, or one of these carbons. Again, doesn't matter if it's the top one or the bottom one. But those are the 2 positions. So what if we had that ether group now over here? It's got those 2 lone pairs. So now, how is this going to be? Well, again, it's not like we can bring that double bond up for the same reason as before. We'd break an octet. But what we could do is resonate that lone pair down to form a double bond. Now the question is, what's going to happen? Do not fall into this very easy trap. When people are learning this for the first time, a very common mistake is bringing this double bond down and now bringing that double bond to put a lone pair on that carbon. This would break the octet of this carbon. All right, you don't want to do that. Resonance structures where we break octets are usually not the more stable ones, right? There's a way to do this where we do not break an octet. And that's just going to be to bring this double bond up over there in the form of a lone pair. And so now we're going to get this guy right here. One lone pair still, positive charge on the oxygen, and he has a negative charge with the lone pair. So again, we got one of the carbons of our diene to have those more extra electrons. That's how the donating group works. All right. What about a withdrawing group? Or actually, some more examples of a donating group first? You can have a nitrogen here. Doesn't matter if it's got CH3s or H's. You can have this group over here, which is probably a little bit more confusing, but definitely one to know. What is that? Right? That's an ester. Right? An ester is this guy. Let me draw it the other way, actually. This is probably I've seen it more this way. R group. So the R group in this case is the diene. All right. So that oxygen here. Oh, and let's draw that. That oxygen, again, same thing. We can't resonate this double bond up over there. It's going to break an octet. But what we could do is bring this down. This guy comes down, and he comes up. Or again, down. And so what we're going to have is this double bond. Positive charge. Double bond here. And a negative on that carbon. Also a donating group. All right. So it's much easier. Do not memorize what are donating groups and what are withdrawing groups. If you understand resonance, it will be much easier for you, because if they give you some weird little, some weird donating group, withdrawing group, and you can't figure out if it's a donating group or withdrawing group because you've never seen it before, resonance is going to help you. All right. Now, one last thing. They can give you guys methyl groups or alkyl groups and ask you if they're donating or withdrawing. And you have to know that alkyl groups, usually it's just a methyl, are donating groups, right? Remember, we talked about in terms of acidity how methyl groups are electron donating groups. Now, in this case, there's no resonance, all right? But what you can do to help you visualize this is, since they're donating groups, pretend that it has resonance, all right? So it's going to put electrons this way, which is going to kind of force this double bond down, and this guy over here. And so we're going to have something that looks like this. Now, this is not a resonance. This is like a fake resonance structure, because technically you should have it positive charge there, because there's no real movement of electrons from that methyl group in resonance, but pretend that it has resonance. Same in this case, if we put it over here, right? Imagine there's some electrons here. These come down. Now remember, do not bring this guy down. Bring him up over there. All right. So if you ever get like an alkyl group, a good trick is just literally put a lone pair on it and resonate that. All right. But just keep in mind that there is no actual lone pair there. How about withdrawing groups? What about them? Withdrawing groups are going to, like the name implies, withdraw electrons. So we commonly see them on dienes. These are dienophiles. So let's draw that. These are dienophile. And we have a EWG, electron withdrawing group. So let's look at this example. One common one that you'll see is something like an aldehyde, like that, right? Or it could be like a ketone. Now in this case, this oxygen cannot give electrons to these two carbons. It has two lone pairs. It can't form that triple bond there because you're going to break the octet of that carbon that has 4 bonds. So it can't do anything in that case. It can't donate electrons to these two carbons, which is what an electron donating group would do. What it instead can do is we can resonate this guy up, and I'll show it in steps. You'll have a negative charge, and you'll have this carbocation. And now remember, we don't like to. What can happen is, now that we have this carbocation right here, this double bond can come up, and we're going to get this guy with a positive charge on this carbon. So that's the goal of a withdrawing group. You want to get a positive charge. You're here. So aldehydes or ketones work like that. Here's another example. We talked about how having an ester where this oxygen right here, let me actually color it in blue, bound to the diene, is an electron donating group. If we have the ester bound this way, it is now a withdrawing group. This is a donating group. So how is that going to look? OR, it doesn't matter what the R group is. It could be like a methyl, OCH3, ethyl. It doesn't really matter in that case. Now we can have it again withdraw electron density. And so let's just see how that would look. Remember, we can't somehow bring this guy in down and then bring this double bond in to give electrons to the dienophyte. We're going to break a lot of resonance rules. And this oxygen here can't contribute anything either because it has lone pairs, two of them. And so all it can do is bring this in and bring this guy out, still not touching any of these two carbons. So what's going to happen is this comes up, and so does that, giving us something that looks like this. On the plus charge on that carbon. All right, so that's another example of withdrawing group. It could be, instead of OCH3 over here, you could have OH, or they could write OR, or another one that trips people up a lot, which is probably one of the harder ones to see, is this group. If they write CN, that's like a cyano group or a nitrile. The way you would draw it on Oscar is you draw a carbon triple bonded to a nitrogen. All right, that is also a withdrawing group. All right, just keep that guy in mind. And so, how do we use these in reactions? How does this affect anything? Right. So, what we're going to have to do is, let's draw an example over here. How this would work. All right. Oh, my mistake. With heat, they could give you they could write heat, or they could write this little triangle, which is just a delta symbol. All right. So how do we figure this guy out? Well, the trick for this stuff, right, is again resonance. Big part of this. So when you have an electron donator group and withdrawing group, what you want to do is, at least when you're starting out learning this, you can maybe, when you get a little bit more experience, you'll know how to do it much quicker. What I'm going to do is I'm going to draw those resonance structures with the donator group and withdrawing group. So remember, the OCH3 is a donator group, so it brings those electrons down. That comes down over here, and this now comes down in the form of a lone pair. So we're going to get this resonance structure. For the withdrawing group over here on the dienophile, this will come up, and so does that. So now we're going to get this. Okay? So you can see that in the resonance structures, we can see that negative and the positive on the carbons of the diene and dienophile. You don't need to worry about what's going on with the withdrawing group or donating group. We're just focusing on the diene and dienophile. So you can see that in one resonance structure, this carbon of the diene has a negative charge, and this carbon has a positive charge in the dienophile. So if we look back to our original structures, which I'm going to redraw, what we can do is we can put a partial positive and a partial negative on those carbons to help us keep track of what's going on. So this carbon in blue has a negative, so I'm going to put a partial negative. The carbon with the plus charge is this bottom carbon on the dienophile. I'm going to put a positive there, which is that carbon. Okay? When we do Diels Alder, the regiochemistry, right? This is the way that it's going to connect. The carbon with the negative has to line up with the carbon of the positive. So right now, this isn't a perfect orientation. So if I kind of take this guy, move him over there, you can see how the ring forms that way, right? If these were better sized. Connect like this kind of, all right? And so the product, remember, draw the 6-member ring. And let's number the carbons. This is a good habit to get into with Diels Alder, numbering your carbons. We know that in a Diels Alder, those two double bonds are going to form single bonds, right? Or actually, one of these will form a single bond. And this guy is going to come over here and form a double bond on carbons 2 and 3. So that's always the easiest thing to draw. So this is usually like the base structure of your Diels Alder, that 6-member ring with that double bond. Renumber 1, 2, 3, 4, 5, 6. Carbon 1 had our OCH3. Carbon 6 had our ketone. And so this would be the answer. Now, there is stereochemistry involved with Diels Alder. We'll cover that in a later video. This is strictly the regiochemistry. All right, and so those two carbons with that partial negative and positive, 3. Oh, sorry, it was 4 and 5. This guy had that partial negative. This guy had that partial positive, right? And so you definitely want to just keep that in mind. This is how we have to handle them when dealing with Diels Alder reactions involving electron donating groups and withdrawing groups. Now let's do another example. They could write OME, the methyl, the ME is a methyl. All right, so that's just OCH3. Now what is CO2ME? CO2ME, so you're going to have to learn some sort of like sometimes these shorthands, and let me put the double bond. We have a carbon bound to 2 oxygens and a methyl. This is going to be this guy, or CH3. All right, this guy is an ester, and it says because that line is going to that carbon, the dienophile is bound here, right? Not to that oxygen over there. So this is functioning as a withdrawing group. So I'm going to just draw that out to make it easier. And let's redraw everything. I like to do Diels Alder when everything is lined up this way. All right. Now you may be thinking, oh, look at this diene, the diene file. It's not in that S-cis conformation. Diene files do not have S-cis conformation or S-trans. That's only something we need to worry about for the diene. Okay. Now in this case, you also see that methyl, and you might think that's a donating group, and you're technically right. But remember, the donating group, in this case, if it's a methyl, it can't even do it through resonance, right? There's no resonance involved, whereas this guy is heavily involved with resonance. So he is going to be much more powerful than that one little methyl group. Now let's draw the resonance structures. Got 2 lone pairs in that oxygen. Brings it one of them down, and now we're going to have to bring this guy onto that carbon. This guy has a negative charge, and we're going to have that double bond there. So our partial negative on our diene is right there on that carbon. Now for this guy, we can bring this double bond up to that oxygen. And we're going to get a plus charge on that carbon. That means the partial positive on our dienophile is going to be right there with this carbon. So you always need to line up the partial positive with the partial negative. All right, this is a very good way to, a very good trick. And so let's number our carbons. 1, 2, 3, 4, 5, 6. Draw that 6-membered ring. Carbons 2 and 3 get that new double bond. So these are 2, 3, 4, 5, 6, and 1. Carbon 1 had that OMe. All right, not carbon 1, sorry, carbon 3. Carbon 5 had, carbon 6 has our ester. So carbon 6. So the whole goal is that you need that partial positive and partial negative to line up. The partial negative was on carbon 4, and the partial positive is on carbon 5. And the one thing we're missing is that methyl group coming off of carbon 5. Here's that methyl group. Now I'm leaving out the stereochemistry. Stereochemistry is involved with Diels Alder, but we'll cover that again in a later video. All right, and so you can see that's how we line it up. The partial negative and positive must be connected to each other. All right, the carbon with the negative always connects to the carbon with a positive. All right, now another trick that you should know, or at least have in the back of your head, is if I know, let me just change up the numbering to make it easier to see. 1, 2, 3, 4, 5, 6. When doing a Diels Alder, right, the regiochemistry, right, so the way that it connects, the electron donating group and withdrawing group, so let me write that, electron donating group and electron withdrawing group must have either, they must be either connected by 1 for regiochem, which you can see here. Let me just erase them. Donating group on 1, 2, 3, donating group on 4. And if you numbered it the reverse, where the withdrawing group on 4 would have been fine. So we had a donating group on 1 and the withdrawing group on 4. That's 1 for regiochemistry. The other acceptable way would have been right here. If I change this up over here, 1, 2, 3, 4, 5, 6. Donating group on carbon 1, withdrawing group on carbon 2. Same if you just number it the reverse, so the withdrawing group carbon 1, donating group carbon 2. That's 1, 2 regiochem. So we must have 1, 4 or 1, 2, right? And that's dependent on how they put the diene. So if they put the donating group here, or if they put it like that, all right? The one thing you cannot have is 1, 3 regiochemistry. If you ever have a Diels Alder like this, you did something wrong, okay? Because if you number this 1, 2, 3, again, if you numbered it the reverse, same thing, 1, 2, 3, your donating group and withdrawing group cannot be 1, 3 regiochemistry. That's bad, right? You have to have it as 1, 2 or 1, 4, right? You don't have to explicitly know that. If you knew how to do the resonance structures with donating groups and withdrawing groups, you would have been able to do it fine, right? Because if you did it right, you'd never get a 1, 3 regiochemistry, right? And so that's how we do Diels Alder with the Regiochem. Next video, we're going to be practicing it more. And after that, we'll get into stereochemistry of Diels Alder. All right, and we're going to be putting it all together, Regiochem and stereochem. See you guys in the next video.